For obvious reasons, this will only be a very, very superficial look at the topic. And I'm not going to try to solve any very complex technical problems here. My goal is rather to spark your curiosity. Curiosity about insulation resistance measurements, which are often underestimated and sometimes not even carried out, and then people just write something or other in the paperwork. Strange things in the reports. So that's my goal. I hope I'll keep within the time limit and that we'll be able to discuss it afterwards out in the hallway. Insulation resistance measurements. It's an obvious topic and everyone here has probably come across it. Where do we carry them out? Well, it's commonly believed that these measurements concern electrical installations, the kind commonly found in homes or offices. This applies to low voltage installations, end user installations. A number of myths have grown up around this because if that's how it's perceived, then the instruments that could be used for insulation resistance measurements on the kinds of objects we see here, well, people think they're determined solely by the test voltage. And unfortunately, as I'll try to show you, that isn't entirely true, because while we may not actually need the kinds of voltages available in more advanced devices, those more advanced devices do have various additional functions that let us speed up the process and draw the right conclusions from the measurements. So as I said, it's widely known that these measurements are carried out, as you can see here, on low voltage electrical installations. And if such an installation is still under construction, like in these first two, on my right-hand side, photos, then these measurements are quite easy and straightforward to carry out. There's nothing complicated about it, but when it comes to periodic measurements, which we perform later on, well, as you can see, the switchboard is packed with all kinds of devices. That can cause problems. And now, while the measurement itself isn't anything especially difficult, what can cause problems is preparing the installation itself for the test. But more on that later. So where else, besides these kinds of installations, are these tests carried out? Well, of course, on various kinds of transformers, large ones as well as small ones like this, or ones like the ones you can see here. On disconnectors, on insulators, on cables. Cables, of course, for low and medium voltage. You should also test stators, which, as you can see in the photo, may be large or smaller. All of this is done using measuring instruments called insulation resistance meters. So how should we proceed? Since I started with low voltage installations, it's worth saying a few words about that as well. How do we go about these measurements? What kind of instrument do we need? What parameters should it have? Well, here this is determined mainly by standard PNHD 6364 Part 6. I'm deliberately still showing here the 2008 version, because that's still the one cited by date in the regulation. So that's why I'm showing it that way. Of course, the 2016 version of this part is also already available in Polish. For low voltage installations then, the test voltage is 500 volts. The required resistance should be greater than, or in the worst case, equal to 1 mega ohm. It's basically a pass-fail assessment. Basically, if that condition is met, then we can consider the installation to be acceptable in terms of insulation resistance. This mainly concerns installation wires. These measurements, just as I showed here in these requirements, we perform them for circuits made with electrical wires. This is just an example, of course. I'm not saying these are the only kinds of wires we measure, but this is an example that's representative of the wires used in installations. In low voltage installations, cables are also used. And for example, a YKY cable like the one shown here is treated as a cable. And this in turn is standard 0.47 and an indication of 2.5 kilovolts. So as you can see in a low voltage installation, there are also cases where 2.5 kilovolts will be needed, not just 500 volts. This is also confirmed by the wording in the SAP standard. And here there is also one benefit. One more benefit. Namely, if we carry out this test at 2.5 kilovolts, then a voltage withstand test is not needed. How does it work? Here we can see an example. A wire, meaning two conductors separated by some insulation. As we know, there is no perfect insulation. Current will flow through that insulation. Of course, it will be very small, but it will flow. Based on the voltage measured here and that current, we'll be able to assess what the insulation resistance is in a given circuit. But two conductors separated by insulation also form a certain capacitance. That's why in these measurements some time is required so that this capacitance can charge up, making it possible to measure only the current that actually flows through the insulation, that leakage current. As we can see here in this example, the minimum required insulation is 1 mega OHM. At a voltage of 500 volts, the current in the circuit, as we can see, is 0.005 amperes, so very small, right? So we need to realize that these instruments must have fairly precise input circuits to measure such small currents. But please bear in mind that at 20 gigaohms or more, at 40 gigaohms or 40 teraohms, those currents will be truly tiny. The method of testing is very simple. We simply connect the positive and negative poles to the given circuit and take the measurement. It just takes a moment needed to charge that capacitance. When using our devices, of course, you can also use accessories here. This is very convenient because right from the socket, after carrying out some other measurements as well, we can also perform an insulation test, of course, after first disconnecting the circuit from voltage. We also have, for these measurements on multi-core cables, other accessories that make these tests simpler and faster. A measurement sequence is possible here, as you can see, where we measure each conductor against every other one, or the live conductors shorted together to the protective conductor. It's quite convenient, and what's more, it can really help because we won't be wondering whether we've already measured this one against that one or that one against another. Or maybe we measured the same thing twice. The problems start in cases like these. You see, sometimes you simply can't disconnect that circuit. And of course, if something is connected to the circuit, even when that circuit is de-energized, it will affect the measurement. The loads connected to the installation will complete the circuit for us, and the results will simply be false, or our instrument may even indicate some kind of short circuit. That's still not too bad, because that in this case will only add to our frustration that despite our efforts, something was still left connected. But what if, like here, On my left-hand side, actuators are installed somewhere in the circuits. Many times I've seen situations where after the tests were carried out, it suddenly turned out that the lighting had stopped working. And that's a problem. Why? Because if we were to apply here, our 500 volt test voltage to these delicate electronic circuits, there are components in there that have to power the device. That can damage them. So that will affect the losses you may incur. So what do you do in that case? How should you approach it? Ladies and gentlemen, this is where the standard comes to the rescue as well. PN-HD 63364 Part 6, what I already mentioned. Insulation resistance can be measured if we short the live conductors together and take the measurement to the protective conductor. A lot of people don't know that. I don't know why. After all, the people who carry out these measurements have to be certified. So some course, some exam, and yet it turns out this knowledge isn't widespread. So if we short the live conductors together, this measurement becomes fairly simple to carry out. What does that give us? Well, if we look at an example electrical installation, this one happens to be a switchboard diagram. And the circuits coming out of it. It's very easy to prepare an installation like this for measurement. After switching off the residual current device, unfortunately, with one pointer, you can't show everything on all the screens at once. Then, after switching off the protection, we can safely measure that circuit. If we short the phase conductor here to the neutral conductor, yes, the phase conductor to the neutral conductor, and take the measurement to the PE bus bar. Simple. Of course, this can't be used everywhere. In old unclassified installations, we have two conductors. Well, in those cases, you can't do that kind of thing, but in TNS or TNC installations, this kind of measurement can be carried out. Where else do we measure insulation resistance? We can measure the insulation resistance of floors and walls. Yes. Or a wall or a floor to assess whether it is an extraneous conductive part or not. You can see our colleague here too, somewhere among us from this photo. So, I can see him right there. Found him. Anyway, he's a specialist in insulation measurements. So at the workshop, you can put a bit of pressure on him too and get him to talk about it. So here we have a method for measuring the insulation resistance of a wall. The second photo is the one in the middle, some kind of workstation there. So we connect one lead to the probe, the second to the protective conductor. And the last photo shows testing the surface resistance of the material the floor is made of. Here, to do that, you need two probes. They are placed 10 centimeters apart. You have to stand on them, and then you can carry out that measurement. This is actually a section of our floor at the company. It's partially conductive because we have EPA zones here, and that's needed to dissipate static charges so they don't affect anything or accidentally cause damage. Sensitive components. Besides, all our production staff wear special garments designed for that purpose. Coats with conductive fibers, wrist straps, special footwear, a testing station. So measurements like that would also be possible here. Where else can insulation be measured? We've been talking this whole time about ordinary installations like these. Well, of course, in PV installations too, even on the DC side. The requirements here are a bit different. As you can see, the test voltages here also go up to 1000 volts. Similar requirements when it comes to the required insulation. but the measurement is performed in such a way that after disconnecting the strings, we can measure the string. I mean the positive and negative poles. First one, then two to ground, to the structure. And that's also possible. Why did I explain it in such a varied way and seemingly so chaotically? Because for all those measurements I just talked about, that claim that you need a meter with the voltage required by the standard may in fact be true. Everything I've shown you here can be done with practically any meter. Anyone that has the required test voltage, you don't need any special extra functions. It's just that what matters is preparing the object itself for the measurements. Here are a few slides. Oh, I forgot to tell you, this presentation contains product placement. So here are a few examples. And that really is true. For these simple things, there's really no problem. You can measure it easily. Accessories. There are quite a lot of them too, a wide variety. All of it is meant to make the work easier. But there are things that start to get more complicated. So what does measurement actually look like here for objects with higher requirements, greater capacitance, where phenomena occur that can help in assessing insulation resistance precisely through the way we record and then analyze those phenomena? So capacitance. The first thing is capacitance. Obviously, we were talking about low voltage installations, but the capacitances there are small. They really get charged almost instantly. Besides, with a 500 volt test voltage in most cases, if the object is in good condition, you'll get a result that says over range. And just as an aside, speaking completely generally here, I've also run into situations several times where a supervising inspector demanded that a specific result be entered because if it says more than 2 Geiger, then he doesn't know what that means. Well, ladies and gentlemen, if the required insulation resistance is 1 mega ohm and the meter shows more than 2 giga ohms, then that's good, isn't it? Of course it is. Of course, in those more complicated measurements, we do need a specific result, if only so we can calculate the coefficients. Absorption coefficients, for example, P or D, but more on that in a moment. So capacitance charging will occur in such an object. That's why at first the meter's entire output will be directed toward that, and a current will arise that will in fact charge that capacitance. But under the influence of the applied voltage, a field will form around that conductor, around the insulation wear. The structure of that insulation, or maybe I'd describe it as the molecules the insulation is made of, they behave a bit like a compass needle, and they'll want to align themselves with the direction of that field. That will also require energy. So there'll be a little current there as well. But what we're really interested in is the conduction current, the leakage current, right? Even if we connected an oscilloscope to such a circuit, we wouldn't see those currents separately. They don't occur separately. What we'll see is the sum of all those currents. And here's the phenomenon that at the beginning, since the current is large, then the insulation resistance indicated by the meter will be low. As the value of that current gradually drops, the resistance indicated by the meter will rise. Here we can immediately answer the unasked question, when should you read the result? Well, when those phenomena die out, or when they no longer have any metrological significance. Because if, let's say, we exceed the meter's measuring range here, then we can wait another hour, even an hour and a half, but nothing will change there. it'll be the same. And then, of course, after the measurement is finished, the circuit should be discharged. These modern electronic meters already have circuits for automatically discharging capacitance. But here's the thing, if we finish the measurement and the capacitance gets discharged, we can't forget about those groups of molecules here that will start to disperse. They'll take on random positions, and what will happen to the energy? That energy will be transferred back into the discharge capacitance. And I had one incident like that. I have a friend who rewinds electric motors. I'll mention him again at the end. He called me on a Saturday saying that someone there touched the stator and got a shock. I got there after 3.5 hours. Well, I don't know, somewhere around that. Big stator, a 6,000 volt motor. Really big. About twice the size of this little pedestal. Only horizontally. And just imagine, ladies and gentlemen, the situation was this. One of his jumpy workers connected the clamps, took the measurement, then right afterward pressed stop and immediately grabbed it to take the clamps off. And he got a jolt through his hands. So the meter had already started the process of discharging that object. Part of the discharge happened through that person. And after those 3.5 hours, when the object's self-discharge process should also have taken place, it turned out there was still over 400 volts at the terminals. So ladies and gentlemen, you need to be careful with that. No rushing, no rushing. To sum up what I showed, that during changes in the current in the circuit caused by capacitance and polarization, the resistance indicated by the meter will increase over time. It's different with a change in the resistance value as the temperature changes. For most of you, that's obvious as well. That resistance will decrease as the temperature rises, and as the voltage increases, it also decreases up to the point of breakdown. That's why in these cases we use correction. We multiply our measured result by the appropriate factor. That's not all. For some motors, 20 degrees is not the reference temperature. For example, the operating temperature is taken into account here. This is simply an example showing that such factors exist and need to be used. Along with these changes that occur in the process of measuring insulation resistance, we can analyze how capacitance and polarization affect the way our indicated insulation resistance rises. Based on that, we can draw various conclusions. It's not so bad if we're taking measurements regularly, for example, on cables, and by comparing them we know whether the insulation is degrading or not, whether those results are changing or not. And here there's also the possibility of an additional analysis of the phenomena that occur as a result of capacitance and polarizations. So as we can see here, curve B, this little graph B, you can infer, because it's not obvious in itself, that the insulation here is in good condition. If, on the other hand, the graph is flat, then you can suspect, for example, moisture ingress. But for that purpose, it's worth having a meter that won't necessarily be chosen only by us because of the voltage, but also, for example, because of the measurement method. As I already mentioned, the currents we're measuring are very small. And current will always choose the path of lower resistance, right? Let's take as an example the insulator we can see here. When measuring insulation resistance in the traditional two-wire way, we won't be measuring just the insulation resistance of this object. We'll also be measuring something else that's a result of the current flowing over the surface. A current I'd call parasitic, but it still gives us some idea, because if we detect that this phenomenon is occurring, then we can decide, for example, that the insulator needs to be cleaned. For example, to measure this insulation properly, we'll need a third lead that will be connected here and will drain off those surface charges. Here, for the example you can see in the photos, we sprayed this insulator with salt water. You can even see discharges here. In that yellow circle, it's sparking, because the measurement is being taken at 10,000 volts. And let's look at what kind of values we're actually talking about for this insulator. Using the traditional two-wire method, measuring the sum of those currents, meaning what's flowing over the surface and the insulation resistance itself, we got 467 megaohms. For an insulator like this, that's pretty poor, right? With that third guard lead connected, we get a result of 900 gigaohms. So please look at the bottom. There's a calculation here. Which current we want to measure and which one is interfering with us. We want to measure 9 nanoamperes. And 21 microamperes is interfering with it. So a much larger current will flow over the surface than through the insulator. These effects have to be taken into account because they can lead to the wrong decision to replace something we think is faulty when it actually isn't. Similar effects occur when measuring transformers and cables. And as we can see here, it's possible to eliminate this effect by connecting a guard lead. In the case of a transformer to the tank, in the case of a cable, you can wrap the cable with a piece of aluminum foil or even ordinary stripped wire. And that's enough. There's also another question. Since all of this is measured with direct current, positive or negative, and where? Well, ladies and gentlemen, an electronics engineer would probably say, what difference does it make? After all, if it's some kind of resistance, then so what? Well, it's not that simple or obvious. Studies that were carried out have shown that in porous materials like these, and perfect insulation doesn't exist, there are effects that mean polarity does matter. I won't go into that phenomenon right now. If anyone's interested, I'll be happy to talk about it during the break. But to sum it up, the recommendation is to connect the negative lead to the cable conductor and the positive lead to the shield. And similarly, negative to the winding, positive to the housing. What else? Sometimes questions come up here about why some measurements differ from one another. As I showed earlier, we're measuring currents on the order of 9 nanoamps. That's already enough. So notice that even if we just move closer to an object like this, we're already introducing a change in capacitance. So these are the kinds of things you really have to pay attention to. And now, why was this whole introduction of mine about the test voltage? Well, ladies and gentlemen, it's because we have 2 meters here that offer a test voltage of 15 kilovolts or 10 kilovolts. And someone will say, but I'll never use that, I'll never need those 15 kilovolts. And where is that even used? Where are voltages like that used? Just to explain, here's the American NETA standard, which shows where those 15 kilovolts are used. But that's not what I wanted to talk about. What I want to say is that these meters have a number of other useful functions that allow for fast diagnostics above all, and accurate diagnostics too. So here, these are the basic functions. Of course, on this topic alone, I could talk with you for hours just about what can be done with this meter. But since I'm running out of time, I'll limit myself to the basic information. So, 40 teraohms is the maximum measured resistance value. Of course, as I said, either 10 kilovolts or 15 kilovolts, depending on which instrument you choose. Measurement time, 99 minutes, well, let's say 100 minutes for simplicity. The coefficients. AB1 and AB2 are user-defined. DAR and PI are already defined and have specific meanings. The measurement current is 5 or 10 milliamps for that 15 kilovolt meter. So just look at how much power this device has. And that lets you charge a high capacitance object faster. It also means you can burn through a fault if there is one in the cable. That power level is already sufficient. Measurements using very long leads. These meters can operate in strong electric fields. We even ran tests here, thanks to the kindness of our colleagues from Gdańsk. And it really does work. They can confirm that. Another thing is the ability to operate while powered from the mains. A large clear display and the ability to generate graphs. And it's those graphs I wanted to focus on, although I've heard people say it's just a gimmick. Only after I explained what it was about did the person who called it a gimmick change his mind. He says he'd been turning a crank all his life and it was fine. Sure, it was fine, but we can't turn our backs on technological progress. So what do these coefficients mean? Just as a reminder, because some of you probably already know. The polarization index, the DAR coefficient, the ratio of the measurement result after 10 minutes to 1 minute, or after 60 seconds to 15 seconds. Why will that matter? Precisely because here we'll be able to observe the effect caused by that capacitance and polarization. What results should we expect? Well, ladies and gentlemen, here's the thing. If it's that first category that's labeled poor, then I'd say that's bad, because resistance really shouldn't be decreasing over time. If something is unclear, then it really is unclear. And okay and good are fine. Then here we can be sure that this is the proper behavior of the object during measurement. And an example, speaking of my colleague who rewinds motors, there was a situation where I simply wanted to get a few graphs and take a few photos, if only so I could put together a presentation like this. Create. So I went to him. I said, do you have a nice stator here I could measure? I do, listen, one that's been rewound. You can see that stator here. It's after rewinding, already taken out of the oven, varnished, all done. Basically perfect, supposedly perfect. And here you can see on the meter, on that hand-cranked IMU meter, that the needle, maybe you can't see it exactly here, that's true, but it's already hit the stop pin. So that was the maximum. Measurements were then taken with my meter, the one that Mika showed earlier. In this case, the 10K one. The IMU did in fact show more than my meter, which read exactly 430 megaohms. And here's the important part. The measurements were taken at 500 volts. So as you can see, a meter capable of generating 15 kilovolts or 10 kilovolts was being used at 500 volts. What did that give us? The DAR ratio was unclear. And that created a problem. So what is it good or not? Well, considering the measurement result of 430 megaohms, very good. So nothing to do but put it together and send it to the customer. But I wanted to dig a little deeper here. So we checked the graph for this motor, and there you go. What you see in blue is resistance. The current is shown in red. The measurement time was 2 minutes. And what do we see? Well, it shouldn't look like that. Indeed, that resistance, the average result sits somewhere around here at just over 400. But here it's obvious something wants to go higher and something is stopping it, pulling it down. Ladies and gentlemen, you probably know how motors are rewound, right? I think everyone knows. Does anyone not know? Well, in that workshop, they jokingly say they just pour the windings into the stator. And there happens to be a woman working there. Equal rights, so she rewinds motors too. And she's been doing it successfully for many years. And it turned out that those slot liners they slide into the grooves here were made of pressboard in this case. One of them cracked about halfway down. And when she was tucking those coils in, literally 2 wires slipped directly between the pressboard and the slot. An interesting situation. What do you think would have happened after the motor was assembled and started up? Do you give it any chance of lasting for long? I don't think so. That 430 megaohms we had was the resistance of those little wires lying there in that slot. Because winding wire is enamel coated, so there was some insulation there, but that enamel would most likely have chipped off due to heat and vibration. A short circuit would have occurred, and that would have been the end of it. So please take a look at what happened after this motor was rewound again. Can you see the difference in the graph? And can you see what insulation resistance value we reached? 12 gigaohms. Here, in this case, the measurement lasted 1 minute. 1 minute because I was calculating the DAR ratio, so even so, this is. And to finish up, ladies and gentlemen, here's an interesting case. So, colloquially speaking, not to throw the baby out with the bathwater. If something is uncertain or unclear, that doesn't automatically mean it's bad. Korean high-speed rail. Just a short little example to finish with. During inspections of these bogies here, which have electric motors in them here, you can see that, right? And they are measured straight away. When a mechanical inspection is done, measurements of these motors are carried out as well. And please note, I know there are some interesting squiggles here, but you can easily read the DAR value. Can you see PI in the table? If there's a cross, that's bad. And note that there's a description here. If that PI ratio was less than 1.5, they rewound those motors. Look, everything lying here is for rewinding, and this is only part of it. What did they do wrong? They didn't take the resistance or the process into account at all. Why? Because if after 1 minute, and this PI ratio is the value after 10 minutes divided by what it was after 1 minute. If after that 1 minute we have already reached an insulation resistance level of around 5 gigohms, then it's very unlikely that anything would change drastically over the next few minutes. And in fact, if you consider only the polarization index, and if you decide that a motor like that has to be rewound, you're just wasting money. Because it turns out those motors were good. Those people only really believed it when there was a completely new motor still in the crate, right? My colleague here, the one I mentioned at the beginning, was there in person and carried out those tests. And in fact, if we rely uncritically on just one factor related to insulation resistance, for example, those coefficients, we can unfortunately make the wrong decisions. Because phenomena like that will not always mean that. In cases where we reach such high insulation resistance values. And at this point, ladies and gentlemen, my time is up. I managed to keep within the time limit. So thank you. Thank you for your attention.